Hi class. We continue our study in chapter 6 talking about quadrilaterals by moving into section 6.3. Section 6.3 is about proving that a quadrilateral is a parallelogram. So we have two objectives in this section. The first one is we want to determine whether a quadrilateral is a parallelogram. And then the second thing we want to do is use coordinate geometry with parallelograms. So we got a couple theorems here. So theorem 6.3-1, and this is converse of opposite sides theorem. So the theorem is this: if both pairs of opposite sides, so this is one pair, AB and CD, and BC and AD, and both pairs of opposite sides of a quadrilateral are congruent, the quadrilateral is a parallelogram, right? So if this side, the opposite sides are congruent to each other, same measure, then ABCD is a parallelogram, all right? And it implies then that it has to be that BC is parallel to AD and AB is parallel to CD here. Another one, all right, this is the converse of opposite angles theorem. If both pairs of opposite angles of a quadrilateral are congruent, so A is congruent to C and B is congruent to D, then the quadrilateral is a parallelogram. So then we must be that ABCD is that parallelogram, and that side AB is parallel to side CD, and BC is parallel to AD. Another one, so this is theorem 6.3-3, converse of consecutive angles theorem. So if an angle of a quadrilateral is supplementary to both its consecutive angles, then the quadrilateral is a parallelogram. So if you have angle A, now it has two consecutive angles. One is D and one is B here. If the measure of angle A plus the measure of angle B is equal to 180 degrees, and the measure of angle A plus the measure of angle D is also equal to 180 degrees, then this quadrilateral ABCD is a parallelogram. So there's three ways that you can show that if you have a quadrilateral that it's a parallelogram. By its opposite sides being congruent, by its opposite angles being congruent, or that it's both its consecutive angles for any angle, sum to 180 degrees. All right, let's work an example. Right, so we got this parallelogram here, right? So for what value of y must this shape PQRS, the polygon PQRS, be a parallelogram? Well, since we are given side values, we look for a value of y that makes both pairs of opposite sides congruent, meaning this side has to be congruent to this side, and this side is congruent to this side. All right, since PQ is equal to SR, PQ and SR, if this is a parallelogram, and both the opposite sides have the expression of x, we start there. So set these two sides equal to each other, like this. Subtract the 2x over like this, add the 5 over, you get x is equal to 6. Once you know x, the second step, you can find y. To do so, we let QR equal PS over here. Well, we know that y is equal to x plus 2, but we know x is 6. So just plug 6 in, and you get y is equal to 8. So for PQRS to be a parallelogram, the value of y there then must be 8, as we see. All right, another theorem, theorem 6.3-4. Right, and this is the converse of the diagonals. So if the diagonal of a quadrilateral bisect, all right, so excuse me, if the diagonals of a quadrilateral bisect each other, right, so when you bisect it, what it means is it cuts this, like this bisector, cuts this so that AE is congruent to EC, and this bisector cuts BD such that BE and ED are congruent. If you have that case, then this ABCD is a parallelogram. Another one, if one pair of opposite sides of the quadrilateral is both congruent and parallel, then the quadrilateral is a parallelogram. So if we're able to show that BC is congruent to AD, so they have the same length, and they're parallel, then it must be the case that ABCD is a parallelogram. All right, let's work a problem. Can you prove that this quadrilateral is a parallelogram based on the given information? Let's explain why or why not. All right, so I'm given that AB is equal to 5 and CD is equal to 5, okay? And I'm given that measure of angle A is 50 and the measure of angle D is 130. All right, so can I prove then by extension that this is a parallelogram? Well, the solution, same side, interior angles A and D are supplementary. That's great. So what that means then is that AB, and forgive the typo here, AB is parallel to DC. And then also, so they're parallel, and AB is congruent to CD. So then thus ABCD is a parallelogram by this theorem 6.3-5. So you're just looking to show with the theorem that, hey, I was able to show that these two are parallel, they're congruent. I use the corresponding theory to say that it's a parallelogram. All right, let's try this one. Can you prove that the quadrilateral is a parallelogram from the given information? All right, so you're given here that KH is congruent to HI, and JK here is congruent to JI. Right, so looking at that, can we say that this is a parallelogram? Well, no. So by theorem 6.1-3, you need to show that both pairs of opposite sides are congruent, which is not what we have, not consecutive sides. So in this case here, we cannot say or prove that this is a parallelogram from the given information. It just isn't. All right, how about this one with algebra? Can we show that a quadrilateral with vertices 2, 6, 9, 4, 10, -1, and 3, 1 is a parallelogram? How can we do this? All right, so there are many ways to do this. All right, I'm going to show you 3 different ways below. All right, so basically showing you how you can prove it with the different theorems. All right, the first one is to show that pairs of opposite sides have the same length using the distance formula. So I need to show that the length of this side is congruent to this side, and the length of this side is congruent to this side. So AB, just using the distance formula here and their points, you take the, so you're taking 2, 9 over here, or excuse me, you're taking 4, 9 over here, excuse me, with the 0.26 over here. So you subtract the x value, square it, you add the difference of the y value squared. You go through the algebra here with the distance formula, you get that that side is equal to the square root of 53. So then what I need to do is show that side DC here also has a distance of square root of 53. So going through with the same formula, the distance of DC using those 2 points gets you the same thing. All right, so now go through it with the other side here. Take side BC, go through the distance formula again. Very simply, you get it's the square root of 26. Now look at its opposite side, AD, going through the distance formula again. You see that that is also equal to the square root of 26. So opposite pairs have the same length. So we're seeing here that AB is equal to DC and BC is equal to AD. So that ABCD is a parallelogram by the first theorem, 6.3-1. All right, another thing you could do is show that opposite sides have the same slope using the slope formula. If they have the same slope, then they're parallel, right? So let's find the slope of each segment. So segment AB has slope of -2/7. Segment DC has slope of -2/7, so they're parallel. Side BC has slope of -5, and slope of AD is also -5. So opposite sides have the same slope. So ABCD is a parallelogram simply by the definition of parallelogram, that the opposite sides are parallel. And then finally, what you can do, you can show one pair of opposite sides is congruent and parallel. So if you look at the slopes and the side segments of AB and DC from the previous slides, you see that their slopes are the same. They have the same distance, so they're congruent and they're parallel. So you can say that ABCD is a parallelogram by that final theorem, 6.3-5.